11.3 polar functions. Now I say here polar coordinates are like, I should say polar functions are like parametric equations. They're not like, they are, right? You have r equals cosine of theta. That's your parameter. That's how it's being defined. All right, pardon me, that is wrong. X equals r cosine of theta. Y equals r sine of theta. So you have an x and y with a parametric function given with the parameter being theta. So they open up a whole new world of mathematics, stuff that you're like, oh, I know how to do this. And then suddenly you get hit with this, and it's suddenly very different. So we're going to plot these and give the rectangular coordinates a polar coordinate system. Looks like this, where each circle goes from r equals 1, r equals 2, r equals 3, and then the angles are given off of there, starting with 0, pi over 2, pi over pi, 3 pi over 2, so on and so on. Now, what makes it different is that I can have two different ways to describe a polar coordinate that are the same, so you have to be aware of that, all right? So 4 pi over 2 would be 1, 2, 3 here, and here. I actually cheated. I knew that was going to be there. So that's polar. Rectangular would be 0, 4. All right. So I just graphed them and worked them out. A lot of people don't like this. They want to know exactly what we're doing and why, but yeah, you're kind of stuck with it. The negative 3 pi, notice the negative means instead of going forward this way, we go backwards, and pi is here. So actually I was wrong. Start with pi, that would be positive 3 backwards. So this ends up over here. All right. So that's pi, and then that's negative 3. So rectangular would be 3, 0, which is counterintuitive. Doesn't make sense. All right. 16, 5 pi over 6. I've been doing this wrong because I'm rusty. Let's go to 5 pi over 6 here and then go all the way out 16. So length of this piece is 16 and the angle to it is 5 pi over 6. So in rectangular world, we're going to get something with a negative and then a positive. Well, this is 5 pi over 6. That means this is pi over 6. We go out, we make our triangle here. Pi over 6 is the same as 30 degrees. So we have a 30, 60, 90. So this would be your short side. This would be your long side. That would be 8. And that would be 8 root 3, which is negative because that's where it's at. So you get negative 8 root 3, 8. And one more. Negative pi over 4, so we're down here. Negative root 2, so we go this way. So that's negative pi over 4. But we went the other direction. We're up here. This is root 2 long. I don't care that it's negative. It's a 45, 45, 90. So one more time in rectangular, negative. Root 2, to go from here to here, we multiply root 2, we divide by root 2, 1 and 1, negative 1 and 1. And if you're ever not sure, you need to look at these in terms of rectangular and go backwards to polar coordinates. So tricky, gotta be on top of it. Graphing is a bit different, to put it very, very, very mildly. So r equals 2. Go out to 2, and we make a circle. Now, this is different than parametric, even though I said they're like parametric, in that we don't have a starting point or an ending point. You could technically say this is where it starts and it keeps going over and over and over on itself, but yeah, that's not the way we look at it. It's just a circle. There's no t. T is not our parameter, so time does not come into play. Radius of -2 means instead of going here, we go here, and yeah, it's the exact same thing. I'm putting them on rectangular planes. Same plane, just how you define it. And then theta equals pi over 6. So it would just be a line that goes like that, which always leads people to say, well, whoa, what about the other way? And I would say, yes, you're correct. Right? That bothers people. It bothers people a lot because they say, well, don't we start at the origin? No, it's just theta equals pi over 6. Everything on this line is pi over 6. This is r equals 1, r equals 2, because it's 2 points, r comma theta, 3, 4, 5, -1, -2. So r could be anything, therefore we're anywhere on that line. Tricky stuff. So more graphing. Now at this point, I would probably get my calculator out. I don't have one handy. Even if I did, I'd be asking a lot. So this is what they call a rows graph. And the 6 means that we're going to have 6 of these little things like this. I'm afraid I'm going to have to graph this. All right, they call that a rows graph. And let's do it on the calculator. Good, we can actually see it. Light's not too bad. Mode, polar. Look what happens to the y equals. So it gives us in terms of r, sine 6. It would be theta this time instead of x. Zoom 6, and we graph it. Can't see anything. Zoom 2, zoom in on it. There you go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. Do I care how far out it goes? Yeah, in the real world, but right now I'm just trying to get the general idea of it. Let's try again. 1 minus 2 cosine of theta. All right. Again, I'm not going to worry too much about the perfection of the scale. There's something funky like that. I believe this is called a limaçon. They put a little funky beard here, I think. I'm not a language person, except for Latin. Amo, amasamant, amamus, amatis, amant. This one here is a circle. Center is 0, 2. I thought we weren't going to worry about, well, I thought I'd just do one of them. And the radius is 2. So what do we just call it? R equals 2? Well, if you notice, it's not centered there. So 4 sine. Notice it looks oblong. Well, that's because we do not have a square background. So if I make it square, now it looks like a circle. We usually go with the standard. So there we go. Some of the graphs. Most of the graphs will be given to you. Use your calculator if you're not sure. Now, how do we convert polar to Cartesian? I was just kind of slapping it together before. Well, here's the big two, without any question. Whenever I have a AP problem and I get lost, I immediately say, well, x equals r cosine. Oh, suddenly I can do it. This is nice to know. It's really good if you're going to be in higher level math. And this is nice to know. These are not as essential on AP. They're essential for me for testing, but not really. So this is why that circle came up before, all right? R equals 4 sine of, I don't know what to do. Oh, well, wait a minute. X equals r cosine of theta, according to this. Okay, well, r is 4 sine of theta times cosine of theta. And by the way, we do a lot of this where we just play with it and we're like, this isn't really helping me. So I look at it and I say, nah, that's really not helping me. Let's cross that out. Let's see if I can solve this somehow. Y equals r sine of theta. Yeah, I can do a substitution here. I know that y equals r sine of theta. Y over r equals sine of theta. Oh, okay, I can sub that in. Come down here. R equals 4 times y over r. Times r, times r. R squared equals 4y. So a lot of this is what I call tricks. I mean, have you seen this trick before? No, then you're kind of out of luck. Hey, look at that. I can get rid of my r. And that's the whole point, is get rid of r's and thetas, so we're just left with that. Oh, okay, I think I know what to do with this. A little bit of algebra here. X squared plus y squared minus 4y equals 0. Add 4. Add 4. Where did I get that? Negative 4 over 2 squared is, yeah, I completed the square. X squared plus y minus 2 squared equals 4. And that's a circle where it's centered at 0, 2, 0, 2, with a radius of square root of 4. Neat. If you're panicking like, oh, I could never do that, don't worry about it. It's not going to happen. Certainly not an AP test, but I'd like to show you what you can really, really, really do when you get to polar functions. It's heavy duty math. So like I said, polar is just like parametric. Just use theta as your parameter. All right. X equals r cosine of theta. R is usually a function of theta. Off you go. Same thing on the y side. But how do we find dy dx? Piece of cake. Dy d theta. Dx d. Hey, this is just like parametric. Yeah, I know. Dy over dx. Double check. Can't be 0. So when you're putting in a value, just make sure we're clear about that. Find it at x equals 2. Let me check the bottom. Ooh, the bottom 0. We got a problem. That sort of thing. So find the slope of the Rose curve at the point theta equals pi over 6. Use the information. Find the equation of the tangent line there. Seriously? Yeah, it's no big deal. Okay. Well, x equals r cosine of theta, 2 sine 3 theta cosine of theta. We're going to take the derivative of that. That's going to be a hassle. Yeah, exactly. It's not a big deal. All right. Y equals r sine of theta, 2 sine of 3 theta sine of theta. Okay, I can do that. We need the points first. Well, yeah, let's do that. X of pi over 6, put in theta for pi over 6. I'm just going to blast it out in the interest of time. Get your root 3. Y of pi over 6, get you 1. Okay, well, what's dx d theta? Well, we need to do y d theta too. I'm not going to do all this. It's going to take forever. Yeah, no, I'm not. I was going to say dy d theta over dx d theta is just in the interest of time. I just want to spend hours on this. You should blast it all out at theta equals pi over 6 and get negative root 3. Nah, I can't be that lazy. I really want to be that lazy. It's just not in my makeup. Dx d theta equals, to leave it, negative sine of theta plus 2 derivative times 3 cosine of 3 theta, leave it, cosine of theta. Yeah, I think I see why I didn't want to do this. This is kind of nasty. Times. Good. Plug in, what is it? Pi over 6. And you get 3 times pi over 6. It's pi over 2. Sine of pi over 2 is 1. 2 times negative sine of pi over 6, negative 1/2. Is that right? Sine of pi over 6, 1/2. Plus cosine of pi over 2 is 0. Yes, that's what we want to see. Everything cancels out. We get -1. Let's try dy d theta. Hope something really nice happens like that. 2 sine of 3 theta times cosine of theta plus 2 times 3 times cosine of 3 theta times sine of theta. We already know the second one's going to fall out. So all we have to do is worry about the first one. Same thing. That gives me 2. Cosine is √3 over 2 plus 0. Wow, it's like I'm good at math sometimes. Yeah, probably just got lucky. So dy d theta is √3 divided by -1 is, there it is, -√3. So at this point, your head's spinning and you're like, am I done yet? I just want to go home. Yeah, well, we still got to do that whole pass for the equation. Y minus y1 equals slope times x minus x1. Y minus 1 equals slope, -√3. X minus √3. Y equals -√3. X minus √3. Why didn't you distribute it? Because I'm not an idiot. Plus 1. Heck, I probably could have stopped at step number 2. Wow. How often do we have to do that? You'll have to do that. That's an AP question right there. I don't think it'd be quite that complex, but pretty close. I know I've done things very similar to that, both on tests and on AP tests. So now for the hard stuff. Yes, harder than what you just did. How do you find the area in polar coordinates? 1/2 r squared d theta from angle to angle. I tell this all the time. People do their best to ignore me. Hey, here's some curve, and here is that's an alpha, and here is beta. The way that polar coordinates calculate area is instead of straight down like we did before, from the origin up in a radial manner. All right. You might not need that for a while, but eventually you will say, huh, I probably should know that. That's going to be important. So here we go. Find the area in the smaller loop of the limaçon. Doesn't have the beard on it, very upsetting. R equals 2 cosine of theta plus 1. All right, first thing I gotta do is graph this sucker. I don't know what the heck's going on. So 2 cosine of theta plus 1. Now, if I go to my window and I look, it starts at theta 0 and goes up to 6.28, also known as 2 pi. So 6. Started there, all right. Started here at 0. Then, looks like it came in here. Then back at 2 pi. Now, here's the hassle. I got to figure out when that little loop starts and when that little loop ends. So let's try this. Let's make it pi. All right. Zoom to there. I got half the loop. So it's at this value here, whatever that is, and 0. It hit 0 a little bit after pi. It also hit 0 a little bit beforehand. So it hits, I need to know when it hits 0. All right, I can do that. That's not too bad. When does 2 cosine of theta plus 1 equal a radius of 0? When does cosine of theta equal -1/2? Unit circle, it's down here somewhere. Cosine is adjacent, so it's going to be here and here if I'm not mistaken. That's -1/2. Oh wait, cosine is negative in the second quadrant, which makes sense, not down here. So that looks like at 2 pi over 3. And 4 pi over 3. So if I've just blown you away, yeah, this is what makes these really challenging problems. I will say the AP usually gives you this information. They don't like you to have to. So area equals, what was that formula? Integral 2 pi over 3, 4 pi over, you know what? I don't believe we did that right. Let's see what happens. 2 pi divided by 3, 4 pi divided by 3, graph. Oh, damn, we did it right. I'm so smart. There's a 1/2. I'm going to throw it out front. You know me and my throwing it out front. And then it's just this 2 cosine of theta plus 1 squared d theta. Only an insane person would try and do this by hand. Okay, yeah, I used to do it, but no, let's just blast it out on a calculator. Careful here. Last time we did these kind of problems, always had a pi out there. Yeah, I thought it was a revolution problem. I thought was, no, just make sure you do what you're supposed to do. Don't forget your 1/2, don't forget your squared, all that good stuff. All right. We could actually do this one by hand, but there's no reason you would never be expected to. This AP problem would be set up, but do not solve. And this is not actually that far out of an AP problem. It'd be one step. You have to be smart enough to figure this out. Probably a calculator problem, so I don't think they'd expect you to figure it out without. All right, how about the area between two curves? You just subtract 1/2 r squared. This has got to have a pi out front. Looks just, no pi out front. Don't do that. Here's the nasty problems that you can see, and they're nasty. All right. In the interest of time, I'm going to graph it and not do all that nonsense we did on the previous problem. Let's see. R equals 1 is a simple circle. And the cardioid, because it looks like a heart, but this one is sideways. Looks something like this. They said if I'm inside the circle and outside the cardioid, so that's this area here. They got to give you a picture. It's impossible to figure out what's going on without the picture, right? Don't worry about it. This is symmetric, so I'm just going to double my answer. And I know this is 0. I'm going to plug in 0 at 1. Here it is. And then it's going to go up to something here. So I'm going to go with 1 equals 1 minus cosine of theta. That's going to give me 0 equals negative cosine of theta. Cosine of theta equals 0. Do a little graph in action. Hey, when is that? That's theta equals pi over 2. So I could go negative pi over 2. I will do that. Why not? Area equals, put the 1/2 out front, negative pi over 2, pi over 2. Which one is further away? R equals 1, so that goes first. All right. 1 squared minus 1 minus cosine of theta squared d theta. Remember, you can use y's and x's and whatnot in your calculator because they're all dummy variables. It's not a big deal. You don't have to get into polar coordinates to do this. Blast it out. If you want to do this one by hand, it's actually almost doable, but I'm not going to. You get 1.215. It's difficult. It's not easy work, but it's doable. We're going to practice like crazy. All right. And now for something mildly fun. No notes here, just showing you. All right. I went on to Desmos and copied this off. See the Desmos up there. And I said, hey, here's some of the more common graphs. R equals constant, a sine of theta and a cosine of theta. Those are graphs. A little bit closer to see that. All right. Your sine of theta is in blue. It's up here above on the y-axis. Sine is always y. Cosine is always x. Then you could have rose curves like we showed you. All right. 2 sine of theta or n theta. You can put whatever you want in there. I think I put a 3 in there and 2 cosine of 3 theta. These got cut off a little bit, but not too bad. All right. You just graph them, see what they look like. I don't have any of these memorized at all, so don't get hung up. Get their limestone curves. So I do have to make a little beard there. All right. And they've got the little, they go all the way around with a little dip inside there. Your lemniscate curves, which are just wrapping around multiple circles. I thought we had a race car curve, but that's okay. They're fun. So that's it for this video. We're going to do some AP problems in a minute. Good luck.